All right, well, welcome everyone to today's virtual AMO seminar. So today we have Jonathan Holm from ETH Zurich to talk to us about scaling quantum computing with trapped ions.
So thanks, Lisa. So it's a pleasure to be here. It's one of the strangest feelings to give a talk. It's 9 o'clock here in Zurich, and I just spent the last hour reading Thomas the Tank Engine and Alice in Wonderland, but it's nice to now try and switch my mind into thinking about physics. And so then let me try and give you some overview of some of the efforts going on in my research group towards scaling up quantum computing with trapped ions. And somehow, just as a flavor to start you off, then I've put this picture. This picture is an unusual chip in our field in a certain sense. There are certain regards in which it's quite usual. You see a gold chip essentially in the middle of a circuit board of some sort, and some wire bonds that attach electrical connections to that chip. But what's unusual for us, or fairly new in these chips, is this bundle you see off to the side, and that's a bundle of about 8 fibers, which are actually all butt coupled into the chip. And that's because this chip both has electrical potentials for trapping individual atoms, but also has optical guides for allowing us to wire up, if you like, quantum computing devices such that we can deliver light from the chip directly to some trapped ions for quantum control. And that's, if you like, a technological flavor in which we're trying to look at how to scale up quantum computing in the approach of trapped ions, which is quite successful at small scales, and the real challenge is to make these systems bigger. So that's going to be the first part of the talk today. And in the second part, I actually want to tell you about a sort of move from the standard approach of trapping, which is often to use radio frequency traps. And in fact, in this device here, you see a little ribbon which brings radio frequency potentials onto this chip. To our thoughts towards actually replacing that with using a large magnetic field, i.e. penning traps, which we think is sort of has potential for being more promising towards scaling these systems up. So I should just start by thanking all of our funding agencies that helped us with this work, if you like. Most of them European, but of course IARPA is a US agency. So, of course, the title of the talk really talks about scaling quantum computing. I'm not really going to tell you about scaling up beyond the biggest devices that we have today, but rather all of the work that we do is embedded within this sort of grand challenge of trying to realize a large-scale quantum computer. And the motivation for that is sort of shown in this sort of graph that we have here. So what's this graph showing? It's sort of taking the size of the problem, which might be in the number of bits required to specify some number that you would like to compute on. And up the left-hand side is actually a logarithmic scale, which is the runtime of some sort of algorithm that you'd like to run. And the types of problems that a quantum computer would be useful for are ones for which the scaling on a classical computer is this sort of white line here. It's an exponential scaling in time that you'd need as the problem increases in scale. And the real holy grail in terms of quantum computing as a device is that fundamentally quantum mechanics allows us to scale in a different way that's sub-exponential for many of these problems. And so even if your basic gate rate is much lower, here it's 10 to the 1,000,000 gates per second, and here it's 1,000,000 times larger than that, then there should be a regime at some point where a quantum computer is able to outperform classical device. And if you're lucky, that will be in a region where the computing time is still sensible. And you see here that it's kind of critical when this crossover appears, because if it appears at a time scale of 10 years, you might not find this a very interesting device. Yeah. So it also marks out that it's useful to think that a quantum computer may be most critically used in problems where you don't have to run it many, many times, but rather a problem where you just want to know the answer once. Yeah? And in a certain sense, that's motivating for physicists, because actually there's many problems in physics, chemistry, materials where actually, indeed, you do just want to know answers of problems in relatively few shots. So what are the sort of problems you might want to know about? One of the problems that's sort of been studied in more depth, if you like, is in molecular structure. So this molecule in the center here is an important part of the process for fixing nitrogen out of the air, which is a process, and it's part of a process used in plant fixation of nitrogen. So this is an important problem to understand the electronic structure of this molecule, because in fact, plants are able to do this process in a much more efficient, energy efficient way than we are able to do it in our modern Haber process, if you like, which is what we use in industrial processes. Yeah. So we would love to be able to discover the more efficient mechanisms by which plants do that. And one of the critical points in the chain of things that plants do is understanding the catalysis that it uses. And this FOMO-CO molecule is a critical part of that chain, but we don't know what its electronic structure is. And we think that by understanding that better, we have a possibility to advance this sort of fixation problem. But one of my ex-colleagues, he's now at Microsoft, Matthias Treuer, a few years ago, along with some other people at ETH, looked at a sort of how many qubits you might need in order to do this sort of problem. And they came up with a number of around 1 million quantum bits and around 10 to the 17 operations. And to put that in context, then the biggest devices that we have around in quantum computing today are maybe 50 quantum bits, and they can do a few levels of gates, so maybe hundreds of gates. Yeah, and that's a long distance between that and 1 million and 10 to the 17, and that's why, in a sense, there's a major focus on scaling these systems up. The other comment I would make about this is that actually most of what this 1 million qubits are doing are just correcting errors that form in the system. So somehow the key element in transitioning from small-scale devices to reliable large-scale devices will be the ability to perform quantum error correction, i.e. Have faulty quantum hardware, if you like, which is able to correct its errors and still produce reliable outcomes. So I'd like to illustrate a little bit about what this correcting errors involves. What is quantum error correction and how does it work, at least in the qubit approaches that we mainly think of today. So I think the sort of principles of error correction are the following in a certain sense. So in physics, most of physics is fairly local. We have interactions with the environment that happen between one particle and its local environment. So somehow the counter to that then is to take the information that you'd like to protect against this noise and store it in a non-local state, so highly entangled states across many particles. Yeah? And if you do that over really many particles, then you need many physical systems for every quantum bit of logical information you'd like to store. And then the other part of quantum error correction is that errors happen with an increased probability over time. And so what you'd like to do is you'd like to repeatedly check for them happening and know and take into account they're happening, or actually feedback on the system to remove them in real time. Yeah. So somehow these are the two principles. First, delocalize logical information over many physical systems, and second, repeatedly check your system. But in checking, what you have to do is you have to make measurements, and we want to make sure that measurements don't destroy the quantum states that we have. So what do? We make fairly local types of measurements, and we only look for correlations. We don't look for the individual outcomes of any one physical qubit, but we rather look, are they all the same, or are they all correlated in a certain way? So actually the minimal sort of code you can think of is in having, I could imagine these little dots here are each individual physical qubits, right? So a trapped ion, each of these in my particular architecture, if you like. And then the idea is you go and measure correlations between these sets of ions, and the minimal code that can store a qubit is about 7 ions. But that's got almost or very limited ability to correct errors. So if you look at any real proposal for quantum computing today, then you should think more in terms of what's the background of this picture. This is a picture that was drawn for one of Rainer Blatt's experiments, if you like, which is somehow this semi-infinite array of qubits extending off into the distance, right? All embedded in some planar lattice. And you would have to be dealing with these and measuring correlations on these all the time. Yeah, and that's sort of the grand challenge involved in making real quantum computers that can produce results. And so you can quantify this. So one of the most sort of generally considered codes today is this surface code, and you can put in sort of heuristic numbers for this and say, well, if I do a gate between two atoms, I could have an error which is already better than any gates that I think anyone did so far today. And you see that what you end up with is about is thousands of ions per logical bit of information you'd like to store in the system. Yeah. And that's really the grand challenge. That's why we think about scaling and scaling in a much different way to the way of just add one more system or two more systems. We have to think both what are the technologies that can take us to this sort of level, and what new techniques or what can we invent that would allow us to go to this level in a more easy way or facilitate us in the scaling. So then let me come back to the physical approach that I choose to follow, right? There are many competing approaches to quantum computing, and I think we're so far from the destination, we don't necessarily know which one's going to be able to bridge this huge divide to get to the final device. But trapped ions are a nice system in the first instance, in a certain sense, because they build on wonderful developments that were made for atomic clocks. And these individual atoms have got internal states that are extremely well isolated. So we can maintain coherence in these systems for good amounts of time. And this is sort of a state-of-the-art picture, if you like, of the common approach to trying to build big trapped ion computers, is that you actually create a linear string with all these different ions in, and you shine in lasers on individual ions when you want to perform operations on these individual ions. And the other key component of this is that here's this string of charged atoms, and they're charged, so they repel each other, right? And because they repel each other, if I push an atom here, then this one moves, and it's a semi-rigid structure. So you can imagine that there's a string stretching between the two ions that connects them in some way. Yeah. So indeed, that's what we do. These lasers we use to produce optical dipole forces. And so if this laser is in a particular state, we can make an optical dipole force that points in one direction. And if it's in the other qubit state, then the optical dipole force can push in the other direction. So on top of that, then we make use of this springy behavior, right? And the notion is really this, that if two ions are in the same state, then they're going to get the same force, yeah? And this will not excite the springy motion. The spring is this sort of out of phase type motion. Whereas if the ions are in different states, you'll see that the forces are opposite on them, and you will indeed excite this spring, yeah? So now the rest of the trick really is to make sure that that excitation of the motion, which depends on the internal state, is something transient, something that happens, but then it goes away after a certain amount of time. And the nice thing is that in our case, that you can arrange things with a certain detuning, such that when it de-excites the motion, and now we're all back in the original state, then there's a phase left behind on the states that were excited, and there's no phase acquired by states that weren't excited. Yeah, and this is equivalent to what we would call a C0 gate, but it's a sort of standard 2-qubit gate, which if you act it on the right sort of product states can generate maximally entangled states. And that's really the key component of trapped ion quantum computing. Now, just to go back to this longer chain, you see that I chose to put these two lasers in on two particular sites. But because this entire chain is a semi-rigid structure, in fact, you could decide to put this laser at any two sites. And if you arrange the frequencies of your lasers and things correctly, you can nevertheless do gates between any two ions in this chain. And that's a very nice feature because it means that even that this ion is connected or is connectable by a 2-qubit gate to say this ion over here, as long as you can shine in a laser beam on each of them at the same time with the right sets of frequencies and so, yeah. So that's been very powerful. That makes these very nice physical systems for playing with, but it's still a challenge to think, and I think nobody particularly thinks that you're going to go to 1 million ions in a chain and scale up all the way to a quantum computer that way. Yeah. So at that point, I might pause because I was told that if there are any questions, I should occasionally pause to answer them. So is now a good time, Alicia, or Dan, to pause? Is any?
Yeah, sure. And again, I'll encourage the listeners to add questions in the Q&A box of the Zoom connection or as a comment into the YouTube stream. But we've generated a few questions. So for example, Alicia Kolar is asking, you know, you showed a picture of the surface code as a really extended but specifically two-dimensional structure. That seems like a poor match for the ion trap strings that you've shown. So is there a version of that that works maybe as sort of a ladder, but is still effective for correcting errors?
Yeah, so I mean, let me put that in two directions. The sort of current near-term angle to that would be exactly the point that I just made, that though this looks like a linear string, it is possible to do gates between arbitrary ions in that string. So the structure is not so laid out on a lattice. Yeah. The second part of that question is that I agree that it would be, or I see that in the future it would be nice to be able to go into more natural 2D with trapped ion systems, and that's the final part of my talk. So please wait for that final talk. Yeah.
Okay. Okay. I guess another question I have is I note that the example you gave in sort of motivating us to want to build quantum computers has a super daunting resource requirement to become useful. So what do you regard as kind of a nearer term target with a potential either for economic utility or maybe scientific discovery?
Mm-hmm. So, I mean, there's lots of interesting devices being built at the moment, which are in a sense, yeah, so these are sort of devices on the tens of qubits level. These are very interesting in a certain sense that a classical computer can't simulate or will soon probably not be able to simulate what they can do. And so in a certain sense, you could say these devices are exploring a larger computational space than you can access with classical computers. Yeah? The main challenge will be that they will be very faulty. Yeah, and in fact, many of these systems are more limited, but already at the 10 qubit level by the errors that they produce in doing anything than they are by the number of qubits you can put into these systems. Yeah, and so they will be very faulty, but that doesn't mean that they can't be, because they somehow explore this larger space, then they're interesting in a way which is somehow as a possibility to access something with more capability, yeah, but not in a very well-defined way than a standard classical device has. And that can be used in optimization type problems. And lots of people are very interested in that. I don't think, I think that'll be interesting in physics. Part of that is just exploring physical models that you can do on these systems. And I think the question, which is not sort of firmly answered, but in physics, we don't usually worry about that too much yet, is whether that can reveal anything really that we didn't know before, right at the moment. Yeah, because we don't know how well these faulty systems can really give us definite answers. Yeah, but of course, physics is like that. We explore, we have these wonderful devices that can go beyond what we can do on classical computers. That's a boundary of physics in complexity. And it's a great thing to be where we are exploring that. I can't tell you if that's currently got an economic outcome. I haven't, nobody's been able to prove that to me. Yeah. But they shouldn't have to prove it to me. I should try it. Yeah, I'm a physicist and I do experiments.
Right. They have to prove it to your funders.
Yeah.
And then a question from Bill Phillips. So are we going to run into a bottleneck also in terms of the overhead of classical computing that would be required to maintain the operation of a quantum computer? So there's going to be a lot of work to measure errors and correct for them, maybe to adapt the specific implementation of algorithms, on the fly to account for errors. Is there a chance that we run into a classical computing barrier in just how to operate the thing?
I think that's not expected to happen. People work very hard on decoding algorithms for error correction codes for these large codes. A lot of those, I'm talking a bit outside my main domain at this point, but a lot of those codes are somewhat heuristic, i.e. they're not always trying to get the exact solution, but rather sort of approximate the solution. And the questions, I think, are usually whether that's in the particular algorithm that's good enough, but I think there's a fair amount of confidence that that should be good enough for the, and it may be that choices of codes also will depend on how well they can be decoded, by a classical computer. So I think it's a big open research question at the moment. In a certain sense, then, if you have a physical architecture that goes slow, you have more computation time, so that's something that if you're a trapped ion person, you smile at, because the superconducting qubits, they go faster than we do by a factor of 100 or so, or maybe more. But of course, the classical computer has to keep up with that at some level, and that may be a hard challenge.
Okay. All right, I think I should let you go on now. Thank you.
Okay, good. Okay, so I've given you a sort of idea of how the sort of trapped ion works in a sort of cartoon way, and I hope I've given you an indication that scaling is a major part of what we're thinking about as we're trying to take that challenge. So I think it's interesting then to look at the technology that's behind what we're doing and how that's evolving. So what you see here on the top left is a trap that, well, I don't know if it's the exact trap, but it's very similar to the trap that Rainer Blatt's been running in Innsbruck actually since the 1990s. And this system is actually one of the most successful quantum computing systems around today. But you see that what this is a sort of millimeter scale structure. So between those tips is several millimeters, and this was made in a machine shop essentially. But still today, if you want to make a long string of, say, 50 ions and put them in a trap and manipulate them, somehow the best performance is still from big devices like this. And the reason is, in a sense, that this string is in a very simple potential. And then you can engineer laser fields, and the technology is quite advanced for engineering laser fields for individually addressing these ions. So the fundamentals of this trap is that there aren't just static potentials applied to these electrodes, but actually on two of these blades, there's a radio frequency potential. And the way these traps work actually is that basically at the center of the trap, the electric field from the radio frequency potential goes to 0. But as you go further away from the center, you get more and more driven motion from this RF electric field. And that effective kinetic energy is what provides confinement, i.e. at the center of the trap, there's no energy of that sort, and away from the center of the trap, there's much more. So it's a ponderomotive potential. But traps in the last few years, as we think about how to scale further, have moved, if you like, between these sort of systems here, which is a pile of sort of 100 micron thick wafers, all gold plated and fixed together, if you like, with now many connections coming in. And what that is an effort to modularize these systems at some level, all the way to devices which are now made with lithography, because lithography, we know how to scale complexity in lithography very much. And you see that the packaging then starts to become also more complex. And at the same time, there's a sort of migration which is gradual from room temperature structures. These sort of systems tend to be run at room temperature. These sort of systems now tend to be run at 4 Kelvin, really for the point of view of getting excellent vacuum without worrying about materials. So in this case, we didn't have to worry about the packaging of this electronics, because we were just going to 4 Kelvin. And also because there's less noise on intrinsic sort of, or unknown source of noise, but noise on the electrode surfaces at that point. So that's the way that traps have progressed. And what you see is there that the complexity of feeding electrical lines to these traps has increased dramatically. But we manipulate these ions typically with laser fields. There's a sort of path of manipulating them with microwaves, but typically it's lasers. And what we haven't really addressed is how to scale up the optical delivery of these systems when we start to introduce higher complexity with the trapping. So that's really what I want to talk to you about today. So one of the things that we try and do as we think about going up in complexity and flexibility is we try and make devices where instead of having very long strings of ions, we try and isolate small numbers of ions in individual zones of a trap, and then bring them to interaction regions where lasers can manipulate them only when we need them for gates. So there's an overhead there. You need to start making these chips that have multiple electrodes and allow us to shuttle ions around. But the overhead I'm going to focus on for now is this one where what you see here is there now has to be 2 regions where light is addressing ions simultaneously. And I, for my whole career, have worked with setups like this. And what you discover as a supervisor in a setup like this, and what you already discovered as a student, is that nobody wants to align laser beams into multiple zones simultaneously and keep those aligned such that you can do really high fidelity operations. Yeah, this is a clumsy setup, if you like. Everything's in free space. Everything's on these adjustable mirror mounts. It's classic atomic physics, if you like, but it's not highly parallelizable and makeable into something that scales. Yeah. So what I want to tell you about today then is sort of recent work that we've been doing with a setup that looks more like this, where light comes from a laser. It goes through a fiber splitter. There are some fiber AOM modulators. And then this light directly comes onto the ion trap chip, and it's then delivered to the ions in the ion trap chip. And here I write it as if these little wires just go straight onto the chip. Of course, there's a vacuum system there. In fact, ours is a 4 Kelvin vacuum system. So there are multiple feed-through stages in order to get down to the 4K vacuum that we operate in. And in fact, this is a picture of the actual chip we used inside or in a cartoon way inside the vacuum system. So we're not the first to set out on this path. So there was a sort of pioneering result back in 2016 from MIT, Ike Twang's lab, Rajiv Ram's lab, and the Lincoln Labs team, John Chiaverini and Jeremy Sage. And they demonstrated Rabi oscillations with light coming through a chip, if you like. And they've recently had results in sort of parallel timescale to ours, where they can now deliver really all the wavelengths that they'd like to use for trapped ion control through some sort of chip. Yeah. Now, the big challenge that they face, and I think they still face it in their latest devices, is that they get a large loss between the input actually to the chamber. They're focusing free space beams onto the chip, and the light that actually comes out and hits the ions. So it's this 33 dB loss. And of course, that means they lose a lot of power, and then they don't end up with maybe as much intensity as they'd like at the ions. Yeah. So I was lucky. Karen Mehta was the PhD student who did this work at MIT, and he came as a postdoc to my group. And what we wanted to do was set out to sort of conquer this challenge of this 33 dB loss and use the extra power then to do the multi-qubit operations, the 2-qubit gates that we had that I showed above. So the devices we have, this is the sort of chip stack up, if you like. So these are silicon substrate chips. They've got SiO2 above them. And then what you would see in these chips are 2 layers of silicon nitride, right? And in different regions of the chips, there are different amounts of silicon nitride. There's then a ground plane layer. We use trapped ions, and they don't like to see charges that move around in this region of the chip. So we have a ground plane. We have windows in the ground plane, and on the top layer, that's where our trap electrodes are. And the basic idea of this is that light comes in on these silicon nitride layers, which are waveguides. It diffracts from these gratings, and it focuses up to an ion that's situated about 50 microns above the surface, yeah, and which is trapped by these electrical trapping electrodes here. So to do this, you can see that that's a fairly complicated fabrication job if you try and do that yourself, and in particular because you have to have high quality waveguides. So what we did was look around for a commercial foundry that could offer some of these things. And with a bit of further development, we found one in the Netherlands, which certainly had some nice silicon nitride technology that we wanted to take advantage of. Yeah. So what we get back when we send designs to these guys is really some portion of a wafer, if you like. And what you see is there are many different traps designs on any different wafer. So I think we get 20 or so back from the foundry when we order them. And then the bottleneck is testing these different chips. So a key technology that these guys had was this double layer use of silicon nitride. And so let me just tell you a bit about why that's important. So here's a waveguide, and what you see is in the square is where the silicon nitride is. It's about 450 nanometers long. And what we're showing in the background is the mode that's guided in that waveguide. So if you make thick silicon nitride, you get a tightly bound mode, if you like. And that's good if you're routing connections on wires on a chip, because it means that the light is tightly confined and you don't lose light when you go around bends. But it's not so good when you're trying to couple light from a fiber, because the mode volume or the mode size of a fiber is very different from the waveguide mode that you typically have. So the nice thing about the fabrication these guys can do is that they have another layer of the silicon nitride where they can make it much thinner. And there the mode is now much expanded and matches much better to what you have coming from your optical fiber. Yeah. So why is that important? Well, because to come from the chip, then we have an optical fiber, and what we can now do is we can basically butt couple it up to the edge of the chip and glue it. Yeah. And then there's an adiabatic taper, which takes us between that edge region and the guiding modes, which are meant to take the light to near the ions. And that allows a good transfer of light from initially a fiber guided mode all the way to where we want them, which is near these gratings, which are going to diffract the light to the ion. So the next part then is that we have to look at this diffraction, and what does the diffraction are these Bragg grating structures. And so I show you a top view of one of these. Yeah. So here's the waveguide coming in, and again there's an adiabatic broadening of the waveguide, which allows the light to adiabatically expand out. And then there are these 300 nanometer period e-beam gratings, and the light diffracts off these, if you like, and it can diffract. You can, by designing the right grating here, you can make it diffract into a mode roughly that you choose. Of course, there's trade-offs in efficiency and exactly how tightly focused these modes are. Yeah. So you see the size of these structures is around 30 microns or so. Yeah. So this is the mode in the first chips that we've been trying, and actually there are measurements here of the mode, and this is actually a real picture. I've got 2 dots here of where the 2 ions should be when we're trapping them for a 2-qubit gate. And in this case, there's sort of a good fraction of the light. It's I think it's 50% of the light goes into this rather Gaussian mode, which has got this 3.7 by 6.5 micron focus. Yeah. So that's basically how it works. We input light from into the waveguides, and light comes out in a rather nice Gaussian beam and hits our ions, which the nice thing about this, right, is that any vibrations in the chip are common mode between the trapping and the light delivery. So we don't have to worry about beam pointing fluctuations or anything like that. So what does the device look like? Here's actually a top view of the device, and actually a lot of work in this went into here. What you see on the left, there's a V-groove array. So there's 8 fibers on this V-groove array. There's a block of glass stuck on the top of the chip here, which allows us more easily to glue the structure together. And then here is the ion trap, and you see the wire bonds coming on top and bottom onto this ion trap. And if we zoom in the middle, then what you see is that this trap has 3 zones. I think this isn't a photo, yeah. But basically the deal is that in the electrodes, there are these little gaps, and these little gaps have gratings which allow you to diffract light out. And in this chip, there's several of those are for 729 nanometer light, which is what we use to manipulate our qubit. And several of those are for 866 and 854 nanometer light, which we repump the ions with. Yeah. So we paid a lot of attention, as I said, to the coupling, and in particular, because we're going to go to 4 Kelvin, this is a job where you need to line fibers up into micron-sized waveguides, and then cool the system down to 4 Kelvin and not change or not lose a lot of coupling efficiency. And so Karen did a really nice job of that. I thought that was about to appear, yeah. So we now get the coupling into the waveguides now is at sort of this 1.5 dB level, and it's maintained all the way from 300K all the way down to 7 Kelvin, yeah. And what that means is that for instance, single qubit gates, then we can get things down now in a couple of microsecond regime for pi times. And the nice thing about that is that the 2 qubit gates actually use the light much less efficiently in terms of the speed of the gate. So the 2 qubit gates are about 20 times slower. And so they're taking now tens of microseconds, and that's feasible to do gates on that time scale. Yeah. So that's the results I'll show you in this slide here. So now with about 1.5 milliwatts coming out of the grating coupler and coming into this mode that hits the ions, we now see what's a very sort of classic sort of Rabi or collective Rabi oscillation that you would see for these Molnar-Sorensen gates. So what happens is that the ion here started in the down-down state. It evolved for some time. Actually here, the ion, there's maximal excitation of the spin. So there's as much spin motion entanglement as we allow here, but that then gets removed again. And at the point where it gets removed, we end up in a superposition of the up, up and down, down states, which I think anyone in AMO physics, you're probably not surprised to know that we're trying to make Bell states. And in fact, this is a pretty good proxy for gate error, is just how well do you produce a Bell state in our system. Yeah. And so what we find is that we evaluate that by a Ramsey experiment on these collective states. And you see that this Ramsey experiment has high contrast, which indicates to us that we get fidelities of these Bell states of about 99.3%. So that's not a record by any mean in trapped ions. So the sort of highest values people have is 99.9%. But I think we were very encouraged because actually we're not really doing anything to try and mitigate errors very hard in this system. So there are all sorts of multi-pulse techniques we could try and apply, but we wanted to characterize really the system itself. And so this is really a very bare gate. And so this is very encouraging that this number immediately came out in a good range actually of fidelity. So we pretty much understand the error sources in this system, and primarily the thing we have as a challenge actually is that the chips, the noise on these chips seems to be high. We don't know if that's our system or that's our chip. So I think that's still a little bit open, but we now have indication that's probably related to the chip. In these chips, what's unusual versus other people doing ion trap experiments in these sort of sizes of traps is there is a window beneath the ions, and there is light coming through that window, and there's also light near silicon inside the chip. So one of the challenges is then to understand that better, and that's something that we're doing at the moment. Yeah. So that's sort of the basic result, that we can now do 2-qubit gates. I think these are the first 2-qubit gates using integrated optics in trapped ions. Now we want to see what other things we can do with those setups. And actually one of the things is that it's actually a rather nice possibility for physics. Yeah. So let me just illustrate that with this example. And one of the challenges in trapped ions is that the trap is defined electrically, and you bring in your lasers through an optical path, right? And so one of the things that's actually quite difficult is to produce a standing wave that's extremely stable versus the position of the ion. Yeah. But on the chip, well, you can divide up the beam into two directions with a very small path difference between the two. Yeah. So in fact, that's what happens here roughly, is that one line gets split up into two. It comes into two grating couplers, and then the light meets at a position 50 microns above the chip. So both of these beams are somehow coming away from the chip, but along the counter-propagating direction, you get a standing wave of light. Yeah. And so we can measure this for the devices that we have, and it all looks like it works pretty nicely. And the nice thing from the quantum computing point of view is certainly that in the standing wave, then you can put your ions either at a position which is a node or at a position which is an antinode. And that's good because gradients of fields tend to be what we use for the gates, but the big off-resonant terms we have are due to, say, having intensity. Yeah. So now what we can do is we can pick out, do we want a large gradient or do we want a large intensity, by just putting the ions at 100 micron difference, 100 nanometer or a few hundred nanometer difference positions. Yeah. So that's, I think, going to be advantageous. We're not taking advantage of that yet. We haven't quite got this chip in the vacuum system yet. But for the Malmer-Sorensen gate, it really removes the major speed limitation type term, which is an off-resonant term which blows up on you as you go faster. Yeah, so that's kind of an interesting aspect. And I think there's probably many ways to extend this. We've actually made chips with orbital angular momentum beams and things like that. And all of that's sort of feasible once you're in this sort of, microfabricated optics game. Yeah, that's kind of interesting. Yeah. So the other thing we're looking at is going beyond just single zone operation. I showed you already that this trap had 3 zones. And of course, these cartoons have many different zones where you see these little dots that are meant to be ions. So one of the chips that we had back from the foundry in that last run was actually one which includes a very critical region for trapped ions. And this goes back to Elisa's question, how do you go into 2D? Yeah. And one of the ways that we think of doing that is having these junctions where we can actually move ions, either decide to move them either that way or that way. And so things get connected together in 2D. Yeah. And so this trap actually has such a 2D junction on. It's a surface chip. And you see there are now multiple zones being fed by these red lights. These are all zones where we could couple in laser light. So a key part of that is this surface electrode junction, which is one of the challenging aspects of dealing with trapped ions, is these junctions. I'll come back to that in a moment. But the other is actually this zone over here, where there are 5 of these grating couplers, and when we measure the modes, the idea of that is to have 5 little beams, if you like, that focus on 5 individual ions in a chain. Yeah. So again, this is a chip we have. We've characterized the modes. We're about to start running that one in the vacuum system in the next few months. Okay, so that's a good point to pause, because I'm going to move on to another topic at that point. Yeah.
Okay, thanks. So we have a good number of experimentalists listening, and once you started showing equipment, the questions have been pouring in. I guess a number of questions are all concerning the maturity of the classical optical engineering technologies that you're trying to bring to bear that are going to be needed for ion trap quantum computing. And I guess, general questions is about the quality of those technologies and sort of what will need it to be, what will have to be developed in this area. So one specific question by Laurent Stevenson is, what are the prospects for fabricating multiple layers of optical waveguides, which you probably need for a more complex 2D chip?
Yeah, I think at the moment I would say I'm not the person to ask about that. Yeah, probably you'd have to go back to the fab and ask them what they think about that. But so I would withhold judgment. Yeah, I think the thing about those nitride waveguides is that they need to have very low roughness, and so it's actually quite specialized the way that the layer gets put down, I think, and it involves, as I understand it, a lot of heating. So I'm not sure how much you want to do multiple layers of lithography. I think, now I say that, but that's probably, may well be that that's the way of doing the lithography that our foundry uses, and it's not clear to me that that's the only way to do the lithography. So yeah, I think I've talked to Sandia people who maybe follow a slightly different approach.
I see, but that's sort of a recognized limitation that people are trying to think of.
It's a recognized challenge. Yeah, that's right. Yeah.
There's a question from Peter with Pawzowski, who's asking about whether you see photothermal heating in your 4K chips and whether that affects the quality of the optics, for example, the focus of the gratings. Yeah,
I don't think we've seen any effect that we could associate with photothermal heating. Yeah, I don't think we see the chip particularly heat up while we're using it, but then we're battling other things. Yeah, so our particular problem is that, as I said, ions are sensitive to charge, and when you put light through glass structures, it moves charges. Yeah. Now there are a few tricks we've played to get rid of that. I mean, the first order thing is that actually even the silicon, we try and keep the silicon as a ground plane, but of course silicon is a semiconductor, and actually when it's cold, it's pretty much insulating. Yeah. But if you put light in, then it starts to activate charges. Yeah. So this was why, in a sense, we put in the ground plane, but we also find that we like to put in red light that's nothing to do with the ions, if you like, to maintain somehow the charge conditions or the amount of light in the chip. Yeah, and so we're playing around with, at the moment, 785 light that's got nothing to do with a transition in our ion, in order to somehow make sure that the charge is in a stable state inside the chip. So we don't see photothermal effects, yeah, but we rather fight charge liberation, I should say, from pulses of light in these materials. Yeah,
right.
So that's
more
the
an
new
effect
challenge
on the ions than instead of an effect on the light.
That's right. Yeah, yeah.
Right. Weiss asks whether you have some characterization of the diffuse scattering of light. It's the chip. I guess I saw that one image of the standing wave picture that looked actually fairly clean, but it would be that when you're trying to get to high fidelity.
Okay. Yeah, exactly. I can probably maybe say something about that. So in this chip, we have these 3 zones. I did have a slide for this, but it's off screen. So we have these 3 zones, and we've done crosstalk measurements where we put an ion in that zone there, and we shine light through this coupler here, if you like. And you might think, if there's diffuse scatter, you might worry that the light gets scattered around and comes back and hits this ion over here. Yeah. Now what we see is, I think 10⁻⁶ levels of crosstalk. Yeah. and we see that it's not due to diffuse light, but is rather due to cross-coupling between waveguides. So actually what's happening is that there's a little bit of light coming out of this coupler when we're putting light through this coupler here. Yeah. So I think what's nice about that is it comes out in a known mode, and it's focused by this coupler. So in the longer term, you think, well, if I'm not using an ion that's meant to be in this zone, I move it to here so it's not in the beam of that coupler. Yeah. But we so far aren't able to see effects of light just, scattering around the chamber that's been coming out of the couplers. Yeah. But it's a valid concern. We just haven't seen it. Yeah.
Okay. Maybe one last question from James Dragon. I guess you have multiple wavelengths of light that are using these same optics. Give you some trouble in terms of the different foci at different wavelengths and needing to track down these beam positioning questions?
Yeah, so I think at the moment we're using it in a rather limited sense. So we do still in this chip have free space beams for Doppler cooling. Yeah. And we do, in fact, the 866 nanometer light so far we haven't been using via the waveguides. But the gratings here are designed such that the I would say the tightly focused light comes from these 729. This is where we really need power because we drive a quadrupole transition. So then these beams coming, the 866, 854 are just not so tightly focused, and I think there's no real worry about overlap of those. There's no real concern that they shouldn't overlap. One thing that is challenging is that in the fabrication, the gratings are put down in a different step to the electrodes, and the electrodes somewhat define the position of the ion. And what it means is that the E-beam step that's used for the gratings actually has to be very well aligned to the step that's used for the electrodes, and that's actually a fabrication challenge that's still, in the early chips, Karam was smart, so he just offset a little bit this grating from this grating from this grating, so that they're all a bit off. But what that means is that you can easily find one that's in the right place. Yeah, so there's still certainly technical challenges to solve in that regard. Yeah.
Good, thanks. I think we should let you move on.
Good, okay. Yeah, so I pointed here to the challenge, and I've pointed to two challenges actually. So one challenge came up in that question, which is in RF traps, the trap position is a function of your electrode geometry, or where the RF null is really a function of that position, and that's very restrictive, especially if you're doing the integrated optics. But also in these RF traps, a big challenge is to do this sort of two-dimensional transport. And that's really why when you look at trapped ion systems today, as exactly in line with Elisa's question, you see mainly linear strings, right? And the constraint there comes from Laplace's equation. So remember I said that the center of the trap, and that's where we like to operate our systems, is where there's no electric field. But we want no electric field and we want confinement. So think about trying to do that in 2 dimensions. What you need is then confinement in one direction, but no confinement in the other 2 directions. And you aren't allowed by Laplace's equation to have curvature in one direction and no curvature in other 2 directions. Yeah. So this is why these RF traps are very often fairly restricted to 1 dimension. People do make 2-dimensional crystals, but you have to live with the fact then that there's a lot of this radio frequency driven motion. And that's a big challenge to deal with in these systems. And to do high fidelity quantum control, I think that still seems challenging. But there are other problems with radio frequency. One of them is that you've got a structured potential, which is a radio frequency potential, and a structured potential which is a static potential. And you have to co-align those on top of each other. And that gets it, if you like, because there are stray charges and things, then in smaller chips, those have a stronger effect. And then this co-alignment becomes an experimental challenge, day-to-day type of experimental challenge. And furthermore, if you think about scaling, then one of the things we already see in chips is that these chips get hot from the fact we supply high voltage RF into them, usually 50 volts or something at 40 megahertz. And already in largish or complicated traps, we see that these chips heat up. And if we start to have much larger areas where we've got active driving of electrodes, this will become a bigger and bigger problem. So you might think to yourself, how can I overcome these problems? And the way I'm going to illustrate that is by starting with work that's still done in RF traps and thinking about the 2D problem. And in the 2D problem, one way of doing it is to say, okay, each individual ion should sit in a potential null, but these potential nulls should be close enough together that these ions can still interact strongly enough. Yeah. So what does that mean? It means you're now making microscopic potentials for each ion, both in the RF domain and in the static potential. Yeah. So what does that look like? How can you do that? You can do that by making electrode structures that are small, yeah, microfabricated, and bringing the ions close to them such that you can get the interaction, the Coulomb interaction, strong enough to get a suitable coupling. Yeah. And the scaling there is that if you can move these ions closer and closer together, then you get a dipole-dipole-like hopping term of the phonons between neighboring sites. And what you find is it goes as one over the distance cubed. So you might like to make this distance small, but unfortunately, in order to make this distance small, you have to make this height small. And that's a problem because there's noise coming from the surface that scales dramatically with height. So this has been done in various groups. In fact, NIST have done a 2-qubit gate between ions in 2 microtraps. Yeah, so this was a very sort of landmark result of that sort. But still, this is a very challenging thing to operate because you've got these two microscopic potentials you'd like to put close to each other. And it's in fact very hard to get this distance small enough to get significant interactions. So that's been a big challenge. So for later, I just point out that one of the things that goes on in this interaction strength is the 0-point motion of the ion. So this is this motion-induced, this is a motional coupling between the vibrations of different ions at different sites. And it scales, if the motion is bigger, if you like, then you get more coupling. And of course, if the ions are closer together, you get more coupling because of the Coulomb interaction. So the challenges in RF traps have been that it's hard to get these ions close together. And there's this heating coming from the surface that limits the height. And what that means for these gates is that they have to go slow because you can't get a large splitting between normal modes. And really what I said didn't say between the lines, but this spring motion is one type of motion of the ions, but the other type of motion is the in-phase motion of the ions. And in order to do the gates that we like to do, you're favored if you can split those two types of motions by a long way, yeah, and isolate them. And in this case here, it's very challenging because the ions just can't be brought easily close enough together. So where ions have done things with 2 dimensions very nicely is in these sort of large multi-ion crystals that you might see at NIST or Sydney, if you like, in penning traps, where also Imperial have played a big role. So the difference in a penning trap is you have a static potential, which in John Bollinger's case at NIST, for instance, is a quadrupole potential. And on top of that, you have a large magnetic field, which is providing Lorentz forces that do the confinement. And I've mocked this up. It's not really a potential, right? But it's related to a magnetic field. So I put it in these squiggly brackets. Right? And so there are sort of beautiful trapped ion experiments that use this, right? They make a large quadrupole potential. So there's an ion trap that's millimeters across, and all the ions sit in that quadrupole potential. And as they, if you like, in the radial directions out to the sides, they can fall down a potential hill, which you see here. This is a mountain, if you like. But as they fall down the mountain, they get the Lorentz force, which then, so the magnetic field points along this direction, so the Lorentz force then keeps them confined in the plane. Yeah. And so John Bollinger produces these crystals of hundreds of ions and does beautiful quantum simulation experiments with these. But actually, this is still a bulk system, yeah. So it becomes more and more complex in terms of its normal modes as it gets scaled. And in fact, to make these nice planar lattices, he has to rotate these at 60 kilohertz. So it's quite a difficult optical task to go in and shine individual lasers on individual sites and do sort of control you'd like with the flexibility for quantum computing. So our idea is to sort of hybrid those 2 approaches, and I think it's then got quite a bit of promising, and also it's made us think of sort of physics aspects of these problems in a new way, so I hope to share that with you. So our approach is sort of going along the micro-trap direction, in that we will make a set of individual potentials for the ions that are static potentials, but now we get rid of the radio frequency field, but replace it by the large magnetic field that's used in the penning trap. Yeah. So again, this is this micro-trap approach. We'll have small electrodes, and we hope to get the ions close together. And so you can ask, why do we have hope that we think we should be able to get ions closer together? And the real reason is that whenever we make an RF potential, it's this pseudo-potential. So actually what we have to do is we apply large oscillating voltages onto the chip, and we use that to make an effective time average potential. Yeah. And if you look at what happens there, the static curvature you can generate on the chip, when that's mapped into how much curvature you get of your pseudo potential, which is what you eventually use, you see that there's roughly a 1/16 weakening of the curvatures that you get there, just due to the ability or the requirement to have stable motion of the ions in this potential. Yeah. So in the penning trap, the nice thing is that we only have to produce static curvature, and we get, for our given voltage, we get all of the power of the static curvature rather than having to divide it by a factor of 16 to get this pseudo potential. Yeah. So that makes us think we can get the ions closer together. We don't have to worry about stray fields in this case, because we're not aligning two microscopic potentials on each other. It's just going to move a little bit our trapping static potential. And this is a homogeneous field, so we don't have to worry too much about our position in the homogeneous field. And then it's nice because this type of trapping only uses static fields. So by contrast with the RF traps, then there shouldn't be any power dissipation in the chips here. There's just static potentials applied to these chips. Yeah? So that seems to be a nice thing from the perspective of scaling. You get rid of some things that you have to worry about, stray fields, and you get rid of power dissipation, which seems like an attractive feature. But it relies on you being able to do these microfabricated structures and get the ions close enough together, and that's sort of the challenge that we have to deal with. So it's kind of interesting to think about motion in a penning trap. So what I'm looking at here is I'm imagining that the magnetic field points out of the plane, and along the magnetic field you get standard harmonic oscillator potential well. But in the perpendicular directions you have this potential hill. And as I say, the ion falls down the hill and it starts to precess. Yeah. And there are two types of motion in there that we divide up into the normal modes. One is this fast oscillation, which is called the modified cyclotron motion. But that also has a precession, which we typically call magnetron motion. And it's actually a weird beast. It's a negative frequency harmonic oscillator. Yeah, I won't say more about that, but that's basically the nature of it. Now, in the standard nature of penning traps, then that's the standard thing that happens. And it's very often the case that this cyclotron motion is much higher frequency than the magnetron motion. So, but you don't have to operate a penning trap in that regime. And in fact, in these micro traps, it seems reasonable to up the confinement frequencies. And at that point, you can get to a regime where these two things are close to each other in frequency. So why is that important? Well, you can look at what the Coulomb couplings are for these types of modes. And what you see is actually a very similar dipole-dipole type form to what we had before, 1 - 3 cos squared phi, that's sort of the angular dependence. And it's again got this exchange frequency, which I was pointing to before, which is proportional to 0-point motion squared divided by the distance between sites cubed. Yeah. What's interesting about that? Well, in the axial motion, this is totally normal, or very similar to what we had for the RF traps. But for these other types of motion, what we see is that 0-point motion depends on the difference frequency between these two types of oscillation. Yeah, and that's very different from a standard oscillator. A standard oscillator, its 0-point motion depends on its frequency, and in the penning trap, it depends on a difference frequency to another type of oscillation. Yeah. So why is that nice? Well, you can think about a regime where you can make this difference frequency small without making the trap frequencies themselves small. Yeah, so it's nice to keep trap frequencies high to reduce heating, but here what we can try and do is inflate the 0-point motion. And so we've been playing with that, and in fact, you get fairly strange motion, right? There's actually both the cyclotron and magnetron motion here. We've set them to the same amplitude, and what you see is that the ion kind of winds into the middle and winds back out again. Now, as it goes into the middle and out again, it climbs up the hill and it goes back down the hill, yeah, of the static potential. And so this is kind of, I find it intriguing. It sort of tells you that the 0-point motion, what it cares about is the time scale over which you explore the peak, the potential energy of your system, which in our case is this static potential hill. But it doesn't necessarily depend just on the bare frequency of the ion, but it's this time over which it explores the potential. Yeah. And this winding in and winding out, the time over which it does that is the difference frequency between these two modes. And that's pretty useful for us. You'll see that in a moment. Yeah. So what does that mean for us? It means that the ion-ion couplings, these motional couplings, are inflated because they're proportional to 0-point motion squared. we couple more strongly our gradients of our fields to our lasers, which is exactly what we want for these 2-qubit gates. And then the bad side to it is it enhances the heating rate, but actually it's an interesting enhancement. It enhances it because also the heating rate is proportional to the 0-point motion squared, but fortunately you don't start sampling noise at this difference frequency, but you rather sample noise at the bare frequency of the ion. So you can, if you keep your cyclotron frequency high enough, and now your magnetron has to be close to it, you can end up with a situation in which you sample noise at high frequencies, and that's a much better thing to do than sample noise at low frequencies. Yeah. So let me just show you how that might happen for quantum computing on a fixed lattice of ions, and this is sort of for calculated parameters that we think are feasible. Yeah. So the idea there is that you might have 90, for instance, ions in a square lattice. That's just a simple example with a 30 micron ion spacing, right? So what you should consider there is that all of these sites have got the same trap frequency. All of them will couple, and you'll get a band of normal modes for each of the types of motion that you have. Yeah. But what we're going to do is we take two of the sites and we say, let's detune these into this critical regime where the magnetron and cyclotron motions are very similar to each other. Yeah. So for those two sites, what you see is then you get isolated normal modes, right, which only involve the ions at those sites. So there are 6 of those because there's 3 types of motions and they're coupled, right? So there's 4 of them here, which are cyclotron and magnetron style motions. And here are the 2 axial motions of those 2 sites, which are also on resonance. So just notice that these are not split by very much at all. They've got a small dipole-dipole type interaction, but these are very largely split because we've gone to this regime of this very high 0-point motion or a very large 0-point motion, and we've enhanced this coupling. Yeah. And so what's attractive in the sense of that, I'm not going to take you through all the figures, is just that when we look at that, this allows you to then, with a laser that just sits at this this half frequency between 2 modes, if you like, get to high fidelities, even in a bulk system, in sort of short time scales in this quantum computing architecture. So I think that comes back to Elisa's question, if you like, how will you deal with these systems in 2D? And this is a sort of new approach to doing that, and I think it looks quite promising in terms of the numbers. So that's what we'll be trying to do. I should just say that you don't have to have a static lattice, and in fact, many quantum computation proposals for trapped ions don't have a static lattice, but rather consider shuttling ions, as I mentioned earlier. This is sort of dating back to Dave Wineland's idea back in the 1990s. And the big problem, as I told you earlier, is somehow to go into 2D. So you do have to do some 2D transport, and what we see is a lot of radio frequency motion in those things. So we really think the penning trap also has advantages there because you just have to move these static potentials to move the ions, and you're not constrained by this need to follow RF 1D lines all over the place, yeah, and break those 1D lines, if you like. So in a certain sense, it looks like you could start to parallelize the transport as well, if you can go down this approach. So let me summarize then. I started by telling you about the use of high fidelity or integrated optics for high fidelity gates. And I've also shown you a bit of the ways that we can look to extend that in the coming years. And furthermore, I have outlined theoretical work that we've done on these micro penning traps and the sort of new considerations that we're having to make there. That's all been written up a couple of years ago and finally got accepted to a journal. And now we're actually building that setup with the help of the ERC. So we move into that lab properly. The magnet probably goes into the lab this week. So that's quite exciting times for that project. So with that also, I'd like to thank the people who did much of the work. So the people in red, Karen Mehta sort of led all the work on integrated photonics and did a wonderful, pretty independent job there, I have to say. He then joined a setup to test that, which was mainly run by Maciej and Chi and Fan Long. Martin Stadler is sort of providing the computer control systems for that. On the other side, the penning trap, I should say that all of these calculations were really the work of Shreyans Jain, who also found some very nice results on invariance theorems and things for anyone who's sort of penning trap related. You should maybe go and have a look. And then the team for that is then involving a postdoc, Celeste Caruth, and Tobias Segasa. Of course, that's embedded in a mostly happy team, right? And I think the support of all of them is necessary for all the results we have. So thanks for your attention. And I look forward to any further questions that you have.
Super, thank you. Let me ask just a few more questions that have come up. Didi Lightfried is asking about how should we now approach with these integrated optics? Is there a is there a solution to the power limitations that will come up when you're going upwards of like 1 million ions? So do you have an idea of how much power such a scale system might require per qubit?
You mean optical power, I guess? Yeah, I think that, yeah.
The RF on the chip, the optical, and maybe the need to transport ions around, like you guys work
yeah,
with
so
like
I mean, well,
budget?
Yeah, okay, so there is a little bit of RF that's used actually for aiding Doppler cooling in these penning traps, and we've done estimates of that, and I think the levels are actually lower than the levels of power dissipation you see on RF traps today. So I'm not too worried about that. It's not really needs sort of millivolts of 10 millivolts of electric potential, if you like, rather than we're used to putting tens of volts on, and there's a huge power dissipation difference there. With the optics, of course, there is a power loss probably coming from losses in the optics. I guess we can estimate that. I think it very much depends on the speeds and things that you do your gates. So in our approach, we use red lasers, right? So we have a milliwatt coming out of the coupler at the moment. We have a rather large spot size, 3.5 times 6 microns. So you can imagine we're not using all that power super efficiently in terms of the intensity we get. But of course, scaling to many channels, I think we haven't done a proper evaluation of the dissipation that's happening in those devices. And how does the light escape? I mean, it goes into some of the materials, and but we don't know what the absorption rate is at a certain level. Yeah. So I think it's relatively hard to quantify at the moment, but we also haven't really tried. Yeah.
Thanks. So Bill Phillips asks about the sort of 0-point motion that you described when the magneton and cyclotron frequencies are almost the same. Should I understand that 0-point motion as the 0-point motion of a quantum object, or were we tracing, classical trajectory lines, and the quantum 0-point motion is actually just some kind of fuzz around those lines?
Yeah, I think, okay, so I probably confused you by showing you classical trajectories. Of course, when the ions are when they've been cooled close to the ground state, they've got just an uncertainty, yeah? There may be I have to think a bit about what's happening with the magnetic field, but primarily you're not seeing big classical trajectories. That would be the sort of equivalent to a coherent state, yeah? But then when I tried to think to myself, like, where does 0-point motion come from and why has it got this peculiar form in the penning trap? I found it helpful then to think about these trajectories, because it made clear to me that this combined trajectory of the cyclotron and magnetron produces this climbing of the potential and dropping of the potential, that the time scale is really given by the difference frequency of the two. So I've drawn these classical trajectories, if you like, to try and illustrate to myself where is this frequency turning up, and in the sense that it's what seems to guide this 0-point motion. Yeah. And so, but no, I think once you're cooled to the ground state, you should almost think like a fuzz, like you do for your, it's a static fuzz, but of course not static, right?
Okay, I'll have to think about that. Graham Stutter asks about, well, thanks you for your talk, and also is wondering about the temperature you'll need to achieve for the radial modes, I think in this penning trap example. And to reach low temperatures or to reach the Lambda-key regime, will you require a laser intensity gradient, or can you cool with the rotating wall drive itself?
Yeah, I think, I mean, that's a bit related to my answer to Didi's question. So we wouldn't use a rotating wall like John does, because we really only have to isolate a single ion on the center of each of these trap potentials. Yeah. But what you do want to do in order to do the laser cooling, the problem with it is that the magnetron motion, as I said, is a negative frequency harmonic oscillator. So what people typically do or some group of people do in penning traps is that they modulate an additional quadrupole that's not the same one being used for the confinement, and they modulate that on top of the original potential very weakly, such as to resonantly couple the magnetron and cyclotron motions and essentially mix them together. Yeah. And then, why is the negative frequency problematic, right? You all know Doppler cooling. What do? You put your laser just below your resonance and you expect to cool your motion, yeah? And in the case of a negative frequency oscillator, in fact, you heat your motion, yeah? So what happens then if you can mix these two modes is that you can effectively Doppler cool by sitting on the red side. And once the Doppler cooling is over, I think you should be in the Lambda-Q regime just as you are for any other type of trap. Yeah, there's no rotating wall being permanently applied at all here, right? Everything is static apart from when you do Doppler cooling, and we see that you get to the standard Doppler cooling temperatures. There's nothing. I'm saying we see, right? We do simulations of stochastic trajectories and things, and we see that everything comes down to standard Doppler cooling limits. Yeah. So in that sense, we're in the same regime as all the ion trap experiments you probably know about. Yeah.
Okay, I guess John Bollinger is following up, asking about specific challenges to get all the way to ground state in pending traps.
Yeah, I think, I mean, as I see it, the Doppler cooling is the thing that's a bit different, but after that, then you can sideband cool. And the problem, as John knows, right, is that you have to have a Raman frequency that bridges your transition difference frequency, and you're in a big magnetic field. So we need then lasers that are phase locked with a sort of 80 gigahertz difference for the magnetic field that we're going to use. Yeah. So the way we're doing that is, well, in the first instance, we generate this light all the way up at 1550 nanometers, and there you can get quite high frequency EOM modulators. So at the moment we're doing that with a sort of beat node lock, but in the future I think we could do it with injection locking. So I think we have a couple of paths to get that splitting. And once you're there, you can do Raman cooling just as we are used to, I think.
Okay, and then maybe one last question related to things that Shimon Kolkowitz is wondering about, and also Bill Phillips. Where do we stand on the fidelity limits at present, and and error corrections, and what do you identify as sort of the big new step to improve that?
Yeah, I think, I mean, the best fidelities that have been done so far were done with Raman gates, yeah? And they have a fairly fundamental source of error, which is, there's a Raman transition you're trying to resonantly drive, but there's an excited state that you would rather not excite into. And so photon scattering forms a limit there, yeah? Now, one thing that I somehow didn't quite notice until recently, if you like, is how nice it is to be working with these quadrupole transitions where there's just no scattering of that type. Yeah. And so, in fact, in our error budget, you would see that our scattering error is sort of in the few parts in 10 to the 5 level. Yeah. Which is just decay of the excited state. So if you can go faster, you can reduce this. Yeah. And the nice thing about that is that we get to that with 1.5 milliwatts of power, which is not a lot of laser power. Yeah. So the challenge in Raman gates, I think, is you have UV lasers and you have to produce then a lot of intensity, and all of that is starting to get difficult. Yeah. So what's the challenge? So my feeling is that the use of the quadrupole transition is very nice. Why did I never really positively think about it before? Well, because the quadrupole transition has this problem that you have to maintain optical coherence over the time of your computation, yeah? And that means you have this you have to produce this fantastic laser, yeah? And then recently we noticed that by mapping, if you like, by starting with a microwave qubit and mapping up and mapping back down, the long-term optical coherence requirements can go away, yeah? And so I think then it becomes my feeling is it becomes very promising to work with these red lasers and deal with those, especially as we can do the integrated optics for these, right? So where's on our integrated optics setup, certainly the challenge is going to be motional. But I feel like then if you ask what's the limiting factor on the best gates that were done today, yeah, partly it's this photon scattering because they were using this Raman approach, but then probably beyond that, it's the sort of stability of optical beams and intensity stability and things like that, maybe funny noise components that are not easy to see or quantify. And again, motional shifts, yeah. So my feeling is that none of that is fundamental. And the emotional things can often be the case of, well, make a bigger trap and you can get rid of them. But that's, of course, and sort of the antithesis of thinking about this long-term scaling. So it's not always that every setup was built just to make the best gate ever. Yeah. And in a certain sense, there's still compromises going on in all of that stuff. So it's a complicated answer. I don't think we're at the limit by any means. And I think, as I say, with the 729, the photon scattering limit goes away. So I think it's sort of, I can see the path, to going an order of magnitude better than the 3 nines we're at today. Yeah.
Okay, well, wonderful. Thanks for addressing also so many questions that the audience had. I think we took you to
Thanks for
town.
good questions. Yeah.
Let me ask Alicia to take over now.
Okay, so what I want to do is wrap up and advertise the upcoming talks. So, Zoom is hiding the controls as usual. So upcoming talks. So next week, the next talk up is our sister series, the Quantum Science Seminar, which will be having Arno Rauschenbeutel from Humboldt University. And this will be Thursday, July 2nd. We are on hiatus next week for 4th of July, and we'll be coming back the week after on July 10th with Dave DeMille. I would also like to call your attention to the VAMOS survey. So we've been up and running for a while, and now we would like to get your input on, which things are working, which things aren't, and sort of where you would like to see this series going in the future. The survey is available on our website, and we'll also be sending up a follow-up email with the link. Thank you very much.
Good. I would say thanks to you all for organizing. It seems like a great thing. Yeah.